By the way, I just wanted to ask the crowd, like, who has seen this thing for the first time on Tuesday? Okay, a good number. So thanks for coming back. I should have asked. So I should have asked at the end of last class, and then had to. Okay, but let me just. This has been a day, so let me just review quickly what we talked about last time. Um, so I talked about gauging as a procedure, right? And specifically, we talked about how to gauge the Z2 symmetry. And we were on the square lattice where all the qubits were on the edges, and I was on the vertices, and then Z2 symmetry is fully X, so it's all right? And I introduced a procedure for gauging, right? And that consists of two steps. First, we introduce gauge field, where it tells qubits for every edge, and we initialize them at 0, right? And then we impose this Gauss law, which is, you can think of like a local symmetry action, right? The product of the Gauss laws, if you product them over all the vertices, they reproduce this action on only the matter field, right? So that's gauging. And then there's a second step which you can do is if there exists a unitary that can turn this Gauss law into a single X, then you can impose that, meaning we can project to the subspace where XB equals 1. And then in this new basis, we only have a theory living on the edges. So you can think of it as a pure gauge theory, right? So you can start, for example, from the eigenmodel, where there are two terms competing, right? You have X on each vertex, or some eigencoupling ZZ, right, for each edge. And there are two phases, paramagnet, which is trivial, or paramagnet, which is spontaneously breaking the Z2. And then we perform a gauging this Z2, and the model we end up is so-called Z2 gauge theory, right? And what happens is in the Hamiltonian, we saw that the X on the vertex ended up as this four-body X on for the four edges around the vertex, right? And the ZZ term ended up being a single Z. So, and this model also had a constraint that we were in the subphase where the plaquettes were all equal to 1, right? So that's why I call it Z2 gauge theory. And there are also two phases in this phase diagram. So I did write it down. One is called the deep and fine phase, where people also say you have Z2 topological order times. And you also have the confined phase, where you can also think of it as a trivial topological order. Okay. And I emphasize that this notion of gauging is different from when I say, for example, condensing the E anion is different from gauging the Z2-1 form symmetry, whose boson ended as this E anion, right? Condensing, although they both end up in the trivial phase, they're doing something different. For condensing the E anion, you sort of go along the space diagram while preserving the symmetry, right? So you go from the deconfined phase to confined phase. But if you gauge that symmetry, you end up with a dual symmetry. You end up back with the Z2 zero form symmetry. And depending on where you started in the phase diagram, you can end up in the following phase. And these two can be reversed. Yes.
Just as soon as I understand the well, so is the difference between the deconfined and confined is the equal action on the ground states?
You could see that if you're on the torus, for example. So this one on the torus will have four degenerate ground states. So you can also think of it as the Z2-1 form is spontaneously broken. That's another way people like to say it. So this is like this Z2 gauge theory. In low energy, the Z2 DQT, right? On the torus, there are four ground states. Other questions?
No, I don't think like thanks.
Right. So you guys, I like to put that in quotes. So when people say condensed E, usually they mean they turn on the Z term, right? And the Z term, what it does is because in the Z, right, it's going to excite the atoms. So what happens is if you turn this on to be strong, right? When let's send this to infinity, what's happened is that your wave function is just going to be a superposition of E's hopping around everywhere. You can also call this the Higgs phase if you want, but people call this confined with respect to M. So M gets defined because M is created with X, poly X, right? And now poly X, if you see in this Hamiltonian, if you want to create a string of X, right, to create M and its endpoint, you'll find that it costs linear energy, right? Because your Hamiltonian is Z. So that will cost linear energy, so M is confined. But the gauge charge E, you can say it's Higgs. So you can also say that this is the Higgs phase. You're in the phase where E is proliferating everywhere. Yeah. So this terminology is just with respect to M. Okay. Any other questions? So last time I think I said something wrong for one of these arrows. I think I was saying last time I said this was which one was it? So here in the Ising model, this part I said correctly. To go this way, you condense these two charges. So you allow these physical charges instead of the gauge charge to proliferate, and you'll end in the ferromagnetic state. To go back to the paramagnet, what you want is these excitations in the paramagnet, they're domain walls, right? They correspond to some different, that's how you excite the state, right? You create these domain walls and you allow them to fluctuate. If they fluctuate enough, you're going to end up in the paramagnet. So in this is a picture in 1D, but in 2D, you could imagine like a region of spin up, a region of spin down around it. You want these loops to fluctuate. And up here, there's a similar story. So this one is a gauge charge. You condense E. But to go back, what you end up doing is you condense some strings. And you might have heard of the word string net model. And the torque code is an example of that. So when people say string net model, the torque code is a condensation of string. What you should think of is here, you're going this way. And it's not that you're condensing the domain wall, that's a different system. Because these domain walls, they're sort of they are not pure excitations, right? They are sort of these quasi excitations that are bound to physical spin. Those are not the physical degrees of freedom that are being flipped. So if you talk about domain walls, you're going to go to the paramagnet. Whereas if you condense these strings, you're going to end up in the toric mode. So that's just a distinction. And last time I think I said condense one form domain walls or something. I should have said one form charges, and one form charges are strings. Yeah, well, I think I said wrong last time. Any other questions about this before we continue? Okay. So I want to continue now. We have a description to, for example, start with a Hamiltonian. Yes. Yeah. So
in your case, we look.
Oh no. So you can still, right? So last time that I mentioned, you can still think of gauging this one form symmetry as a certain type of condensation, right? But gauging is, you can think of it as you introduce a system with the dual symmetry. In this case, suppose we want to gauge this D2 pointing to E. I introduce a system with the dual symmetry, which is paramagnet, which is zero form. That's actually the two form gauge field. And then I condense. So this has a physical charge, physical D2 charge, and we call it C. And I condense E times C as a bound state. So after the condensation, you're going to end up with just a system with D2 zero form symmetry, and the E gets identified with C. So you can also think of gauging as a type of condensation. In this example, you sort of end up in a trivial state. So there's nothing interesting. But for example, suppose I started and said with, let's say, a diagram within theory. It has some twists, right? If I condense E, I just end up with a confined phase. There's nothing left. But if I perform the gauging, I still remember what the dual symmetry is. And although it's featureless, it still is in an SCT phase. So you can see some response to a background gauge field. So that's sort of the difference. This thing allows you to remember the dual symmetry such that you can reverse it. Whereas here, once you're in the confined phase, if you want to reverse it, it's not canonical. Like, how do you go back? You can either enter back into the one with a trivial twist or non-trivial twist.
Can it be the same that and different?
Right. Because it's just, you can think of it as, with this symmetry, with the Z2-1 form symmetry, there's only one trivial phase. Yeah. But there are two ways of spontaneously breaking it, and those are the two that I got. Okay. Any other questions? Right. So last time we saw how to do this at the level of the Hamiltonian, but today I want to go one step further, which is I want to actually see this gauging at the level of states and operators explicitly. So what are we going to do is I wanted to, so just to recap this part, what we did was we started with some theory with the on the Hilbert space, let me call it HB, which is just a tensor product of all vertices. Maybe let me write it like this. The number of vertices. And then we ended up with some theory on the edges. Number of edges. Right. So we started with this Hilbert space, ended up with this Hilbert space. So I want to define a map that does what this gauging does. So I've seen a good example. I'm going to write down a definition. So I'm going to define gauging map as the following map from vertices, number space to edges. This is for a Z2, we're gauging Z2 zero form symmetry. And it does the following. Suppose I have a wave function defined on the vertices. What do I do? Let's follow this procedure. So I start with my psi on the vertices. I add these ancillas, which are in zero on the edges, right? And then I impose this Gauss law. But a different way to think of imposing this Gauss law is first, I perform a basis transformation. Now in this new basis, Gauss law is just x. And then I project to xv equals 1. So what I can just do is apply this u, and then project into the plus state for every vertex. So here, shorthand is plus for vertex is just all the plus states, right? And here all my edges. Okay. Right, so you can even write G as an operator like this, although I find it a little confusing. As if you're taking an expectation value of something, but note that this is a different Hilbert space from this. Actually, this is a map. So it's like a vertices and edges with 0, right? And then the plus. So it goes in here and comes out there. This is huge. So this is a map from the vertex Hamiltonian, the vertex Hilbert space to the edge Hilbert space, right? And it actually has a kernel. So you're actually going to lose some information. I'm going to show how to see this later. But so it turns out that for example, the subspace, if you're in the subspace where your Z2 symmetry is -1, then any state in this subspace will be mapped to 0 through this gauging map. So it'll be gone. Gets killed. And also it has a co-kernel. So anything where your one form symmetry, what was my notation? Well, one form for each, one form for E. It's -1. There exists some gamma such that this is -1, then it'll also get killed. So the map is only, so G is only unitary, turns out to be unitary, but in the subspace where this thing is equal to +1. So if I restrict HV to the subspace where the 0 form symmetry is +1, and then I map it to edged over space where I restrict the one form symmetry be +1, we're all looped down. And I'm going to show this in a moment. What?
Okay.
Oh, eta is this cross.
Specify what it was.
Oh yes. Last time I did, but this time I did not get them. You ready to again. So U was the map given by we take all edges and you look at all vertex edge pairs that are next to it. You're saying, and there's some operator called control X. And what it does is it maps XB it's an order 2 operator, and XP is invariant. So it's this order 2 operator that acts on the polys as follows. And as a matrix, 1, 1. So if the vertex qubit is 0, you do nothing. If the vertex qubit is 1, you apply polychemical. Yeah.
If I remember correctly, last time you also showed us how to gauge by gauge fix.
Yes.
And then you would set it. And maybe you also elaborate on this, I just thought, but this way, where you use the phases from
Right.
Would not work all the time.
All the time, yeah. Right. So this gauging map's only well defined if this unitary exists. Yes, I agree. For the purpose of this talk, I'll just restrict to the cases where this exists. In general, it might not, but yeah.
In the case you have to do gauge fixing, you cannot put it define this much.
Yes, that's correct.
It's possible to find an interest that realize the gas law. Like I think that's something in your case, you're not to correct.
Right, I'm not adding anything.
They're just
Yes.
your symmetry is visualizable in a very strict sense.
It's a very specific sense, and so I can always do this. So it's sort of assuming your matter field transform under the regular representation, something like that. That's what I would be assuming, going to the non-Wheeling cases. So that'll make my life easier. And then this U will exist, and then I can define a gauging. Yeah. So how do we see that fact? So that's how it acts on states, right? That's the Schrodinger picture. Now, actually, you can also see how it acts on operator. And for that, I want to do is, so G has a kernel, so I don't want to really conjugate an operator by it. I will rather, what I want to say is, suppose I have some operator A on the right side of G, I can push it through G, and it becomes some other operator B. So A and B is ambiguous up to things that get killed here, or things that get absorbed in here, right? So there's some ambiguity. But this is just, you can push A to some operator in B. And I will denote this as A gets sent to B by G. So this is my shorthand for this. Okay. So let's see what happens. So for example, so let me do the calculation here and tabulate the answer there. So for example, let's see how XV gets pushed through, right, if we use this formalism. So this is this U, and then I have XV, right? So XV, I can move it through here, right? This is just H. And now when I move it through U, what's going to happen is, once I move it through U, this X is going to become this phi body operator. So each edge next to it is going to have an X now. And now I'm projecting out X on the vertex on the plus state, right? So this thing gets killed, and now everything is on the edge and I can push it through. So then I now just get that becomes this times G. Okay. So X under G gets sent to the vertex. That's what we expect, right, from up there. Let's do it for this two-body DZ, right? Same thing. Now notice that there's some trick you have to do here, which is if I just push this through, it'll actually commute with you. I can just push it through. But then it gets stuck there because this is a projection on vertices and these guys are on vertices. So I cannot push it all the way through. So the trick you have to use is you have to use the fact that you can pull out a Z on this edge for free because this state, all the edges are in the zero state. Okay. So then now I can push it through, and what happens is using that map, for every vertex with a Z, it's now going to be gone. So I'm going to get single Z on the edge. I push through. And then I'm going to end up with just single Z times G. So my eigenterms in Z under the gauging map becomes Z on an edge. Now actually from this, it's already enough to see how everything else maps, because it turns out that everything that is, for example, Z2 symmetric is generated by a single X curve and a DZ curve. So for example, we can see why this map has a kernel, because if I take the product of all vertices, right, under the gauging map, this will map to a product of all vertexes. And this is equal to 1. Right. Which means that anything that you can only map stuff that is where this thing is enforced on this side. So that's why we have to restrict to that subspace. Okay. And so we're saying that, and this is a statement that the zero form symmetry has been gauged, right? In this subspace, it does not act anymore. And now we can also work backwards. Suppose I have Z here, right? So if I consider the Paquette term, then this will just map to 4 Ising term. Right? And they just all cancel pairwise. So this is also equal to 1. Right? Which means that I have to be in the subspace where all the Paquettes are equal to 1. And then also, or the non-contractible loop as well. Well, they have this long string, right? It comes from a bunch of Ising terms auto cancel. So this is also enforced to be the one. So here it's saying that we going this way, we engage the zero form config, right? And then here it's saying we're go back, we engage the one form symmetry, so that it's non-trivial in the subspace, but when we map back, it becomes trivial. Okay. So what have we learned? Okay. How does so what is this? So if we restrict to the subspace, right, where zero form is plus one, the one form on this side is zero plus one, then these two Hilbert spaces. Oh, why did I say unitary? Did I say I saw them because these are different subspaces. These are different Hilbert spaces. So it's isometry in the subspace, right, where you restrict the vertex to the zero form symmetric sector and restrict the edges to the one form symmetric sector, right? And it's an isometry. And moreover, we have that the XV and Ising term, right, has the same commutation, relations as this vertex term and this Z term. Right? Whenever this anti-commutes with this term, this will anti-commute with this term. So sometimes people say they just in the physics literature, some people will say they describe the same so-called bond algebra. It's just that they live in different Hilbert spaces, right? So if so but embedded in different tensor product Hilbert space. HV and H. So in the subspace, they're exactly the same, right? But now we enlarge it to the full tensor product Hilbert space. And so you will find that there are operators you can compute, for example, for this operator, what is the commutant in the respective Hilbert spaces in this enlarged Hilbert space? And the commutant exactly is what captures these guys, right? So the symmetry here, you can also view it as there are different commutants of the same algebra, which would have been the same in the same restricted Hilbert space, but when you enlarge it to different larger tensor product Hilbert space, they have different commutants, and those are your symmetries. And to map them, you have to kill the both sides to make them match, right? And that you can think of that as gauging. Right. And so one nice thing about thinking of this way, is suppose I have a Hamiltonian made out of these terms, out of these operators. In the description subspace, they're exactly the same. So they have the same spectrum. So for example, if you restricted the Ising model to the even sector and periodic boundary conditions, and also restrict your Z2 gauge theory to the one form symmetric sector, then they have the same spectrum. But when you enlarge it, you can still get a degeneracy coming from the symmetry. For example, although in the paramagnetic phase, there's one ground state, right? In the toric code, if you're in a deconfined phase, you're on a torus, there are 4 ground states, right? So this only shows up in the degeneracy of the spectrum. And it's because, right, you can say that this one-form symmetry is spontaneously broken. So then to go between different sectors, you have to apply these one-form symmetries have different expectation values. And you can, that's how you tell between these different ground states with different degeneracies. But if you restrict to the subspace where they're all +1, then it's exactly the same Hamiltonian, just restrict the subspace, it has the same spectrum. So that's why we can learn about, for example, when there's a phase transition in the Ising model, we also know there must be a phase transition in the V2 gauge theory. But the degeneracy can change. But when it becomes critical, will be the same. Like, so the phase transition point will be the same. Right. Well, it can become a bit more subtle depending on how the symmetry acts at the transition. So for example, if we did this in 1D, we know that there's a paramagnet and a ferromagnet, right? And they get swapped under this gauging. But at the Ising critical point, there's only one ground state. And that one ground state is still one ground state. It doesn't become 2 ground states in the astral gauging. Because kill out something, but then other sector comes in, right? So you have to look at like what happens among all the sectors. Be able to tell what the ground state is. Okay. Any questions so far? Yeah, I want to keep this split so that you can compare. So now I want to do just another example that demonstrates this point. So so far we consider bosonic system. I just want to give a cool example where we consider fermionic system. So many of you might care about real nature. So you might ask, what does the spin? What are the spin system? So I mean, this will be a bit closer to nature, but so let's consider gauging a fermionic symmetry. And I'll just do the smallest one, which is V2, fermion parity, as an example. And okay, so instead of a spin system with a qubit, I'm going to replace each vertex to be complex fermion. Right, with the creation and annihilation operator, they obey anti-commutation relation. Right, and for this, it'll be useful to define my Majorana operators. They're real fermions. That's called gamma. And there are 2 of them. And these guys square to 1. And they obey these commutation relations. Basically, they anti-commute whenever there are different types. And when there are different species. Okay. So whenever they're not the same one, they anti-commute, basically. And on each side, we can define the fermion parity, which is fermion number mod 2 minus 1 to the fermion number. And it turns out you work what that is in terms of Majorana operator, what it is. So it's just a product of the two Majorana operators. Right. And there's an I here because I want this to square to 1, that these two anti-commute, right? So when I square it, I need extra I to help. And fermion parity, so gamma of Majorana is fermion parity odd, right? So on the same side, they're going to anti-commute with each other. That's the relevant algebra. Okay. Maybe I should have written that there. Now I'm out of space again. Yes. Gamma. Did I miss some factor of 2? Maybe there's 2 here. Is that what you asked?
Yes, but also, so the first and the third are the same, that line. And I think maybe they should both, there should be no prime.
Oh, yes. This one, when it's a different site, it always, yeah. So I should have a different one. Let's see. This is always, sure. Thanks.
I think you should have all
Did I?
on the first one. Yeah. On the
Yeah. Yes. Okay. Too many times. Okay. Okay. So now I want to consider. Yeah. So consider a system with. I'm going to call this symmetry fermion parity F, and it's defined as this product of all vertices fermion parity on every vertex. Okay. And now we now know that from this gauging map, I actually don't need to tell you what the Hamiltonian is. You can write down a Hamiltonian if you want later, but all that matters is the algebra of operators that is symmetric under the symmetry that you're talking about. So the algebra of symmetric operators, I can just specify them. And you can write any Hamiltonian you want made out of these operators. And after gauging, you just need to figure out how these operators map, right? And those would be the gauge Hamiltonian. Okay. Operators. So that's generated by fermion parity itself. And now on each edge, I can have, instead of an Ising term, so instead of X, I have fermion parity. And instead of the Ising term dz, I can think of this as a hopping operator. So secretly, they're made out of C and C dagger, right? But I just want this to be unitary. So you can write it in C and C dagger if you want, but this is just a unitary version. So then it's making my life easier. So it's just basically, you can think of it as hopping from one site to another site. So gamma, gamma prime, and gamma, gamma prime. Let's say I choose this convention. Right. You can wonder why I didn't choose gamma, gamma, but that just differs by adding a fermion parity here. So this choice will just make my life easier, and we'll see it in the mapping. This is just my convention. And it turns out that this generates everything. Anything fermion parity, even you can think of, is generated by a product or sum of these objects. Okay. Okay.
Sorry.
Yeah.
So it's 2i over there.
Sorry. Here.
Oh no, sorry. No, never mind. Sorry, it is 2. Yeah, sorry, I got confused. Yeah.
Okay. So now let's gauge fermion parity. Good. Let me do that here. Gauge fermion parity. Which is now. Maybe let me use a different color so you can see what I'm doing. Gauge fermion parity now is product of fermion parity on every set, right? We can still introduce a gauge field, which are qubits for each edge that remain the same. And now I impose the Gauss law. I just change this to fermion parity, right? Can you see the blue? Not.
Looks like white.
Okay, let me use red. Gravity is states. Okay, fermion parity. That's the only thing I need to change. And now if there exists a U such that this Gauss law is now fermion parity, then I can project fermion parity to 1. It turns out that this U exists, but it's more complicated. I won't try to write it down, but if you want to see it, it's in this paper. For U for gauging fermion parity. Okay, so I won't write it down explicitly. But let me tell you, once you restrict what the final gauging map is. So go back to 1. So the resulting gauging map is given by the following. So you can sort of see that because I did a basis transformation that turned PV into all P's, right? Sorry, turn all this into a single P. So now P will also map into P times all the vectors around it. Then I project PV equals to 1. So what will happen is PV will get mapped to product of 4 x's. That's still the same. Okay. But now we want to map these two-body hopping operators. Now, naively, you might think, I'm supposed to get a poly Z E here, poly Z vertical edge here. But then notice that the Majorana algebra is different, right? In the eigencase, these ZCs, they all commute, right? So that's why the algebra operator, if it anti-commutes here, sorry, everything commutes, right? So this suffices. But now notice that suppose I have a gamma, this hopping operator here. And let's say I have this one here, right? These two actually anti-commute. So how do you see that? When I move this through, right? One way to count it is this gamma prime and this gamma prime is actually on the same vertex. So they actually commute. So you subtract one commutation out of all the other anti-commutations. You move 2 through 2, you get 4 anti-commutations. But actually one of them is commuting. So actually it's secretly 3 anti-commutations. So the way to count it is how many sites overlap. So this actually anti-commutes. So this will not suffice, right? So the way to fix it is, for example, and you can show that there will be a map that does this for you, but the final answer is you put an X here. So then that will solve that problem for you. Now Z will anti-commute with this guy. But now there's also another position, which is here. So these two also anti-commute because this side overlaps. And I will put that X, solve that here. And you can check that that's all. So these two operators will have the same anti-commutation operators as this. Okay. And now let's look at the constraint of the product of fermion parity under the gauging map, the vertex term, which is again 1. So it means that we have to, for this map to be an isometry, we have to restrict to fermion parity being 1. So we've gauged fermion parity. Now, what is the symmetry on the other side? Right, similar to on that side, we had a one-form symmetry corresponds to hopping P. Right? Now, what happens on this side? Now you have to. It's a bit harder to guess from this side. But what you can do is, for example, you take these hopping operators I wrote down and product them around a plaquette. Okay. And you'll find that, okay, these two will cancel, but these two, they don't cancel. But that's exactly fermion parity. So let me also put fermion parity here and fermion parity here. Now everything cancels. Okay. And now, so you just have to map what this 6 operators maps onto this side. Let's do one example. So suppose, so I will have a zx coming from this edge, another zx coming from this edge, and then this one, I will have zx, x, and then I'll have a fermion parity which maps to the vertex term. Let me just write AV. And there'll be an AG here. Okay, and you have to clear up all these cancellations, but then you will find that this part, let's see. Yes, it'll be times A. Okay, so instead of the usual plaquette term with V, there's an AV attached down here. Okay, so you can see this AV cancels these 4 x's, and then you get a AV here and the usual product of C. So that's the plaquette term. And then now you will also have the normal form. So for example, if I take a string of gamma gamma 5, right? In the Ising case, they cancel, but here I also have to put in fermion parity on each vertex so that they all cancel. So when you map that through, that'll become something like that. Okay, and then other things. The last one. So what is the symmetry on this side? So notice that in the toric code, right, you hop an E with V, right? And you hop an M with X. So this thing, what it's transporting is actually a bound state of E and M, right? So the symmetry actually corresponds to a product of this Z2E times 1 form M. So let me call that M, right? So it's hopping the fermion, which is the bound state of E and M around the clone. So the symmetry on this side, you get fermion parity. On this side, right, you end up with a symmetry whose endpoint is the fermion. And that sort of makes sense because we're gauging fermion parity, right? That's why we end up with a symmetry whose endpoint is the fermion. So unlike gauging a bosonic symmetry, you end up with one form whose endpoint is a boson, right? In this case, it becomes the fermion. Okay. So an interesting claim is the following, that this Z21 form, and maybe let me mention that instead of imposing that the plaquette term is 1, right, that's your usual gauge theory. Now this is a weirder gauge theory where you impose that the product of the vertex and the plaquette term is 1. And you can also think of that as instead hopping a fermion around a closed loop. So you're enforcing the fact that you're hopping a small fermion instead of hopping E, right? So it's now hopping F around closed loops, and that has to be 1. So this is the gauge theory. It's a weirder gauge theory, but you can define it. So it's a different Hilbert space in this subspace. Okay. So this operator eta1F is a V2 one form. And the claim, so here's an interesting claim, it is anomalous. So if I only had, so if we started with the spin system with this symmetry, and I tried to gauge it, I would run into a problem. So by anomalous here, I mean there's an obstruction to gauging. So let's see what goes wrong. So the problem is you cannot find Gauss law that make that commutes. So if I have that global symmetry action, right? Maybe I want to break it down into some local symmetry action. Maybe I want to say I define my Gauss law, right, for each edge. Maybe I want to define a local hopping operator, and then I attach, what's that, right? I attach this the two-point gauge field on the vertex, like what I did with the gauging usually, right? And then that one, I can also break it up. For example, suppose I did it like this. This is my FP. And then I hop it. And then I attach the gauge field here. Right? You see that this one doesn't commute with this one because this edge anti-commutes with this. So you see a problem that, and it turns out there's no way to fix it. So you cannot, with only polys, if you attach these, there's no way to make this consistent. So you cannot impose a local symmetry action that all commute with each other. And so there's obstruction to gauging the symmetry. So it is anomalous, and it's coming from this anti-commutation. So this is just an example, but you can show that there's no way to fix it.
Okay, we have by gauging, we will see the application for that.
Yes.
What you're saying is this is one to see the observers.
Yes.
It's not.
It's not gaugeable if you only have bosonic degrees of freedom. What I'm going to show next is if you have fermionic degrees of freedom, then you can gauge it. Right, so then you can go back. Right. So the claim is that this V2 one form in the present in a fermionic system is gaugeable, but it's not gaugeable in a bosonic system. Yeah, that's
You stash some setting.
Yes. So I'm suppose we forgot we had fermions in our system. So I'm just saying if we had a bosonic system. Yeah, that's the claim. Yeah, then it's not gaugeable, and it's because this one that does it horizontally and commutes with some of them that goes vertically. Yeah.
So for example, this would be to take the first down and multiply the Gauss law.
Right. I'm just doing the same formula where I want to define a local symmetry action. So I introduce these gauge fields in an attempt such that when I product over all this, it reproduces the global one, right? So all these cancel, and I get this long string back. But then I find that this version that's vertical, horizontal, and this version that's vertical, they're not compatible. So I cannot do it. Yes.
What was wrong?
Suppose I
Add this.
Yes.
What would be the problem?
Oh, because I want to impose this Gauss law, but they don't even commute in the first place, so I cannot restrict to a common like eigenspace where they're all plus one. Yeah. actually, there's a fun remark. If if we only gauge in one-dimensional submanifold. For example, instead of gauging a whole space, I want to gauge this one form symmetry only on this line. Then there's no obstruction because I only need to impose these guys, not these guys. I only need to impose the horizontal ones, and they all commute. So this is not anomalous. This is in the high energy literature. This is known as higher gauging. So you gauge on submanifold instead of the whole manifold, and it turns out that in some cases, even though the symmetry is anomalous, if you try to gauge in the whole space, in the subspace it is gaugeable. But this is just a reminder. And as a fun fact, so note that if I started with fermion parity, right? After the gauging map, if my Hamiltonian was just fermion parity, which just means that my system has fermions, it's just empty, right? I end up with the state, which is also the toric as a ground state. It's a different Hamiltonian, right? And we'll end up with a Hamiltonian which is A B, something like this, and then minus this term that I'm constraining, which is A B times B. So this isn't forced to be one. I can put it in energetically, but in the low energy subspace, this is still the toric as a ground state. It's just that we're enforcing fermion loops to be one instead. And so in this toric you can actually gauge this in a subdimensional manifold. And what you end up getting, you can work this out on the lattice even, is that this line here then becomes a EM duality defect. Meaning that when you have E and you push it through, it becomes M on the lattice. So maybe if you want to try this as an exercise to show that you get an EM duality if I just gauge it on a single line. So that's a one initial point.
But is it on the submanifold line kilowatt?
It's kind of, that's why it's called this higher gauging, right? It's like it's a zero form symmetry in 1 + 1D.
Okay.
And it turns out you might know the fact that in 1 + 1D, there's no anomaly for gauging fermion parity. Oh, sorry, there's no, you can always do bosonization, right? In a 1D line. And you cannot distinguish fermions and bosons. So this anomaly is coming from the fermionic statistics in 2D, but in 1D, you cannot tell fermion statistics. So that's why it's anomaly free. That's why one way to think about it.
Sorry, so where's the second term come from? And
This one?
Yeah.
This one is if I want to get that non-local term up there, the one that goes around the other vertical cycle. Yeah.
Thanks.
And so, right. So coming back, yes,
That whole system to the point connection with
yes,
the system has verified
yes.
you gauge it,
Mhm.
and the resulting symmetry is not gaugeable.
If you didn't have fermion, yeah. So now if we have fermion, but if we have fermions, it is gaugeable.
I think you start with the first step to the gauge series and you modify the Gauss law and okay.
Yeah,
That would be an example where you have bosonic.
yeah. Just start with the infinite system. Suppose, yeah.
The way we should actually fix that. Not that we got there by gauge, but
Right.
could have gotten there.
Yeah, but most you forget about.
That's the problem, like the correct concept.
Yeah.
It imposes this weird Gauss.
Yes. Yeah.
It's still like
That's still a valid spin system. It's fairly bosonic, and suppose there are no fermions, you would run into a problem of gauging it. But now, if you remember that we had fermions, you can actually use fermions to help get the right Gauss law. So the correct Gauss law with fermions that allows you to gauge it is you replace these guys with So here's a funny thing. It's that you replace your, usually you add a two-form gauge field, which is bosonic. Here you add a two-form gauge field, which is fermionic. And somehow that allows you gauge. Because these two, the commutation of these two hopping operators is exactly the same commutation of these two hopping operators. So then the effect of the anti-commutation actually exactly cancel. So then, and then you can gauge it. And then what you end up is, you end up with a fermion. So sometimes people would also say, I don't prefer this choice of wording, but you say you can gauge it, but you end up with a fermionic system. I prefer to separate it. It's like you cannot gauge it if you're a bosonic system. If you are a fermionic system, you can gauge it. Oh, and I should give a reference for this, which I forgot. Switch these two up. Before I erase this, let me just mention this gauging map is called the, let me use a different color, called the exact organization map. By UN Chan, and and you can do this for arbitrary high dimension. You can do this in any dimension on the lattice. And you can generalize this to arbitrary triangulation also. You have to be more careful. And then you need to learn about cup products on the lattice to get, and then you can talk about spin structure also, how to get spin structure right on the lattice. This reference.
How would it be possible to track read small homology? No, like what you're based on numbers.
Well, how do you tell?
Is there like, yeah, is there a way to get a
Right. So, I mean, you could use the fact that they're in this fermion lines. That is one way to tell. And you can see that from the hopping operator, where you do an exchange and you find that there's a minus sign. So it turns out this minus sign, that is the frustration, has the same origin as the minus sign coming from exchange statistics. So if you do the exchange statistics on the lattice and you see some sign, that is a indicator of the anomaly. Let me erase. Okay. So I'm done with this example. And now I want to switch gears actually, the last 25 minutes, and start talking about how we can use gauging to get symmetries themselves on the lattice. Symmetry from reality. Under gauging. So let me start with a continuum picture first. This is 1 plus 1D maybe, but big in anything. And let's say you have a theory T, and might be familiar with this notion of gauging half space. So take your half space, form a gauging, right? And maybe your symmetry is A, and the resulting theory called count T mod A. But then this thing might be secretly, when it's equally isomorphic back to T itself, right? You can apply the map, right, to map both sides back to T. And then the thing that arrives here, we call that a duality defect. Right. Okay. So let's apply this to the lattice. So the example I'm going to do is we're going to go back to 1 plus 1D now. So I'll do the 1 plus 1D new model, where you have now instead of vertices, I'm just going to write them as an index j, being integer. And I'm going to set, okay, and then let me not set it yet. So if we perform gauging, what I'm going to get is this term turned into a single Z living on, maybe let me do. Yes. I do gauging, I get Z now living on the edge. Let me denote that with a half site. They might have. Edge, gauge, and now, but we know that if J equals to H, there is a re-identification we can do. So what we can do is we swap D and X, and we also shift J minus 1 half to J. So I want to identify all the edges back to the vertices. One way I do it is I shift everything by a half a second. Okay. So then this becomes, so if J is equal to H, right, I get this one becomes Zj plus 1, Xj plus 1, and then becomes Bj. So the individual terms don't actually exactly match, but I'm summing over all J. So on a periodic chain, it's the same Hamiltonian. Okay. So that's this picture here on the lattice, right? So I've shown that there's a sequence of things you can do such that you start with the same Hamiltonian, you end up back in the same place. Okay. So we can define the duality, the Kramer-Swannian duality. As an explicit operator, as the gauging map, right, composed with some identification W. So W is something like this, roughly this half shift composed with swapping action. Okay. Yeah.
I swap. So if you want to make W really a linear map between different spaces,
Yes.
you're mapping like 0 in plus and 1 in minus.
Yes. Yes. So the operator on each site, I will call it, well, usually people call it Hadamard in quantum information. This map X plus Z over V2. Yep, and it maps 0 to plus 1 to minus. It's just a Fourier transform basically for Z2.
But 0 belongs is on the edge, while plus is on the.
Right. So then there's this part which is a unit term, and then there's a re-identification. That part is just different Hilbert spaces. So it's just a map. But the gauging map was also just a map, but you compose it with this hatch, it now becomes an operator from HV to HV again. So now I can call it an operator. Before, if I didn't do the identification, I cannot call it an operator. I cannot call it an operator. It's just a map. Yeah. But, yeah. So this is an operator on my vertex over space. And moreover, it commutes with the Hamiltonian. So commutes with Ising. H Ising if J is for the H. If
Can I go back a little bit? The part of the last one, so you added the other, I mean, three of you really all of you, right?
yeah.
Can we interpret this via anomaly flow?
If you only had a bosonic system, then there's an anomaly inflow. Sure. I can say a bit about it. So the bosonic system, it's a D2-1 form. It's anomalous. And it flows into a 3+1D theory whose action is something like E cup B. B is a Z2 form. But if you have fermionic system, then this is not anomalous. You can also write down a lattice model if you want that matches this anomaly. Okay. Let's see, I have 15 minutes. So let's see how far I get. But basically, what I wanted to get to was I wanted to show you a graphical way of writing this operator down using pictures by just drawing pictures. But it's going to be starting a new topic, so let's see how far I get. And I think I can try to get to the main point where we would derive what this operator looks like, but see how far it gets. Yes.
G is the gauging.
Use a gauging map. And W is this hash shift times atomite.
So I'm first stating the theory and then I will do this.
Yeah, and re-identification. So only this is just a map. When you combine it with this, it becomes an operator of the same Hilbert space, within the same Hilbert space. Right. So in 2D, there's no such thing. You cannot map edges back to vertices again. There are too many edges. So there's no such map. So this only exists, say, in 1+1D. Or in 3+1D, if you get your 1 form, for example. That's another example where you can go from edges to faces on a cubic lattice because they're equal number. Okay. So let's see how far I get. I want to show you a graphical notation for gauging duality. And this comes under many names. The broadest name may be tensor network. This is the word used a lot in kinetics matter. In quantum information, the specific thing I want to talk about is called DX calculus. And the math thing, the math people will call this Frobenius algebra. So hopefully you might have heard of one of these names before. Okay. But I will not use any, I will stick to this notation, but hopefully if you're familiar with the more mathy notation, you'll recognize how it's, if you're a more math person, you'll recognize what I'm doing is like a Hopf algebra for Z2. Okay. So I'm going to introduce some graphical notation. So are people familiar? Is anyone not familiar with graphical notation? Oh, who is familiar with graphical notation where half? Okay. So basically, I can have a tensor with many legs, and each leg is an index. Are people familiar with this sort of kind of picture? And if I have two tensors, I can contract them by drawing lines between them. This is like Einstein summation, right? You sum over a repeated index, something like that. That's sort of the notation I'm going to be using. And for this, I'm going to be defining two tensors. One, I'm going to use usually on a whiteboard, I call this a black dot, but let's call a fill circle. It can you call it black? Okay. It can have many legs, and suppose it has n legs. I'm going to tell that this, for example, I can think of it as a state. So suppose time is flowing up, right? This is a state, right? As a ket, and I'm going to think of it as all 0 plus all 1. I'm going to ignore normalization. So for example, this has 4 legs. This is just all 0 plus all 1, like a GHZ state, just like a ferromagnet. So, right? Okay. And I'm going to have, and you can think of this, suppose I have this with 1 leg going down, 2 legs going up. What it's doing is, if I input 0, it's going to be mapped to 0 tensor 0. If I input 1, it's going to be mapped to 1 tensor 1. So you can think of it as copying. Okay. And the second map, I'm going to use a plot. So this is, and there could be many legs. And this is going to be all plus all minus. And if you expand it in the 0, 1 basis, it turns out it's going to be, suppose I say this is A, B, C, E. This is just going to be it's just going to be a delta function where addition mod 2, 0. So I'm going to call this a sum tensor because if I input A and B, the output will be A plus B. Okay. So if you're already familiar with the Hopf algebra, this is the multiplication and co-multiplication of the group's algebra Z2. Okay. And it satisfies some nice property. For example, let's see which one do I want. Let me just that. And it doesn't matter whether they're kets or bras. I can flip them up and down if they like. One property is that if I have, yes.
Like 0, 1, 0, 0, 1, 0, 0. I put 0, 0, 0, 0. I just add the digits. That would change that.
Oh, this is addition mod 2.
Yeah. But I just add the digits that the string belongs to and output.
Yeah, this is just a qubit. So 0 and 1. So 1 and 1 with a 0. Yeah.
Okay, and if I have multiple, all of this.
Yeah. I'm not doing multiple. And it has some nice property. For example, if I have this big tensor and I contract it, this is just going to be a bigger one with the same number of legs. Same for this tensor as well. And you can see that because it's all 0 plus all 1, if I connect them, then the 0 on this side has to match on the 0 on that side. So it just becomes the same tensor with a bigger number. The same thing also for this guy, same type. And here are some other things. You can ask, what is this guy for one leg, right? That's just 0 plus 1. That's my plus state. What is this guy with one leg? That's plus, plus, minus. That is my 0 state. Up to normalization. I'm ignoring normalization everywhere here. And there's some other rules, but let me get to the punchline. I'll introduce the rules as they come along. So I want to write down first the gauging map using these operators. So recall that in 1D, what you do is, let me do one more thing first. So let me do an example of a unitary. I take this guy and I contract it with this guy. And what this does is, suppose I have state A and B here. A is going to get copied. And then I add B. So it outputs A plus B. So this is exactly this control X operator I said previously, because if this state is 0, do nothing to this state. If this state is 1, flip it, meaning you added 1 to it, 1 to. And you can also see how the polys map through this by some identities. Oh, maybe I should write it there. Some other identities. Because this is 0 plus all 0 plus all 1, right? You can think of it, this is the ground state of the Ising model. So if I apply spin flip poly X on all legs, that does nothing. Also, if I apply an Ising term, which is these on any 2 legs, that also does nothing. Okay. And for this one, the rules are reversed. If I apply V on any all leg, does nothing. And if I apply X on any 2 legs, does nothing. So now let's do the gauging map. How do I write the gauging map with these operators? So I start with an arbitrary wave function on the vertices. Right? And then I initialize my state on the edges with 0. And then I perform this unitary. And then I projected out each vertex in the plus state. And then I have an output on the edges. So that's how it would look like in time. So this is my gauging map. But now we also know that this unitary is made out of these smaller gates. And we can put them into this formula. So if we now use that notation, I still have my 3 vertices ingoing. My edge is in the 0 state, which is that plus tensor with 1 leg. Okay. And it turns out this unitary acting is for every vertex edge pair, going where the control is the vertex and the thing is the edge here. So it's for every vertex edge pair, like this. Correct. And then finally, I project it to the plus state. Which, oh, sorry. I think it project to the plus state. which is the solid dot. And then they up like that. So it's a map from vertices to edges, that's the gauging map. So now I can simplify it. Using that rule that I can fuse the same kind together to get a bigger one. So for example, all this fuse in this whole column fuses to one big block, and also this one. So for each row, you can just fuse everything together, and you end up with something that looks like this. Okay. So this is explicitly my map from the vertex to the head. That's my gauging. Okay. Let's check that it does the right thing. If I have a poly X here, we can use those rules to push it through. So for this solid tensor, X acts on all edges, does nothing, which means that if I have an X on one edge, on one side, I can push it to X on the other two sides. And then for this one, we have if I act X on two edges, it does nothing. Two legs, I should say legs. So it means I can also push it from one leg to the other. So X gets maps to 2X. And also the similar for, I should have done. You can also check with DZ by a similar picture. You have mapped to a single Z. So it does the right thing as a gauging map in one. So how do we get the Kramers-1 in duality? So let me suppose I want to get Kramers-1 in. What I do is now I apply so-called Hadamard gauge. So this is my symbol for it, which swaps X and B. And then I do a half shift from vertex. Okay, and so now this is my Kramers-1 operator, explicitly as a diagram. And if we push things through further, X will become B now. Let me see up here. Right. B. And then DZ gets pushed through, becomes X. So we can show explicitly that mapping, right? That X maps to DZ, DZ maps to X with the correct indices. Any questions about this?
Is it something like a class with only one leg is the unit and dot with only one leg is the unit?
Yes, yes. So, right. So this one will be 0, which is the unit. And this one, which is the plot cap, is the co-unit. And it's just because we just use the property that these guys use is equivalent to the fact that it does nothing. There's an extra rule actually that when you have two legs, this is mapping, plus to plus. This as a state is just like it's mapping plus to plus and minus to minus. So it's just identity. So I can remove the symbol. Yeah, and the fact that they fuse is just already encoding associativity in the get-go. So maybe let's stop here. So we derived the Kramers-1 operator explicitly as a picture. But now, next time, what I'll try to show you is we can compute things with it. For example, I can square this operator and try to simplify diagrammatically, and we'll try to derive what the fusion rule of this operator is. And second, we will try to generalize this to more general settings. So if you're using Hopf algebras, you can go to non-abelian groups, for example, and see what happens. Now you can also gauge non-abelian groups using a very similar formalism. Yeah, and then I'll try to end with subtleties about matching these symmetries that we created from duality defects on the lattice to the continuum. And many of these subtleties are related to this sort of hash translation.
Yeah, so it's very capsule. So
You have to gauge what's it.
So for gauging the capsule, matrix, so that was still it's like equal once in a while first.
Yeah, I think it's hard. I'm not sure because the gauge fixing is you're in the wrong Hilbert space, and then you do another projection back to the right Hilbert space. So it feels a bit awkward.
So like when you gauge in the continuum, typically you need a bit less than hope algebra, right? Like it's enough like Frobenius symmetric delta separable.
All right, that's if you want to gauge a subsymmetry. Right? Here I'm gauging a whole symmetry, and it turns out that any anomaly-free fusion category is a representation of a Hopf algebra. So this turns out to be the natural way to gauge rep H, which are all the anomaly-free symmetries if you gauge the whole thing. Yeah, but I agree, there are sub-algebras, subsymmetries that you can gauge inside of things that are anomalous. I won't talk about that.
Also,
Where this unitary does not exist. Sure. Maybe I can tell you offline about it, but I can tell you the construction. If you have here's one fun thing that you might want to think about. Suppose I have a stack of 1D Ising models in the ferromagnet, so ZZ, and I gauge for every nearest neighbor pair, there's a diagonal Z. If you gauge this, you'll end up with a toric code you can show. So if I have ZZ as a Hamiltonian of each chain, and I don't gauge, so if I gauge it individually, right, I'm gauging the Z2 to the L, I'll just end up with a trivial state. But if I gauge Z2 to the L minus 1, meaning I gauge only the diagonal ones, I'll actually end up with a toric code. And there you cannot do a gauge fixing because you're gauging to not the whole symmetry, but only part of it. So you cannot simplify this into like a stack of 1D things. Turns out. It's a fun exercise to try to think of.
No,
I don't think I ever know. Oh.